Good morning from the home offices of the Nittany Mountain District. I'm here this morning with my assistant, Scouter Jameson, and my name's Josh. I'm the Senior District Executive for the Nittany Mountain District, and I'm here this morning to do a fun STEM Nova experiment with you to help some of you Cub Scouts out there work from home on some of your STEM Nova requirements. So we'll be talking about requirement 1C for the Science Everywhere Cub Scout Nova Award. 1C is an hour of reading and watching anything related to science and making a list of 2 questions about what you watched and turning those questions into a STEM Nova counselor. Obviously we won't be doing this for an hour, but this will be part of that time spent will be in this video here this morning. We'll also be working on requirement 3A, part 5, and that is choose a scientific question that you would like to explore, investigate and explore. Choose a scientific question you would like to investigate and explore it. So the scientific question that we're going to explore here this morning is why oil and water don't mix. And to do that, we are going to make a lava lamp. So some of you may have seen a lava lamp at home, and those lava lamps you plug into the wall. It heats up, causes a chemical reaction, causes bubbles to bubble up through the tube, bubble back to the bottom, and start all over again. As long as that's plugged in and there's heat and that reaction is happening, it'll keep bubbling. Well, today we're going to do something kind of similar, but our lava lamp's going to be homemade. And this lava lamp works with the following items. These are things you can pick up at your local grocery store. I don't think that the pandemic has wiped these items out yet, at least not at my local grocery store. You will need an empty bottle. Any empty bottle or jar will do. For you really little Cub Scouts, you might want to use a jar with a wide opening on the top to make it easier to pour things into it. I like these sparkling ice bottles because of the shape. They look kind of like a lava lamp. They're really handy. You can get those at most grocery stores. You'll need some vegetable oil. Most people have this in their kitchen to do cooking with. There's still lots of this left at the grocery store, so if you need it, you can go out and get some. Water. We're going to use bottled water here this morning. Easiest thing to do is use your kitchen sink. That way, no spills, you got water available at the faucet. But we're going to use bottled water for our experiment here this morning. Food coloring. You can pick this up at any grocery store. We have several different colors here this morning. Red, green, yellow, blue. The darker colors seem to work better, so for this morning we're going to use some blue food coloring. And the last thing you need is Alka-Seltzer tablets. Any kind of antacid tablet will do. Generic brands work just fine and are a lot cheaper, but we need some kind of an antacid tablet to cause our chemical reaction. So those are the items that you'll need. If you're not going to use a kitchen sink, wash tub works great. That way you can do the experiment pretty much anywhere in your home. So back to our scientific question that we're going to investigate and explore this morning, and that is why oil and water do not mix. There are 2 reasons why they do not mix. The first reason is because of density. Okay, so to explain density in a way that I think we can all understand, density is when molecules are packed tightly together or not packed tightly together. So think of a stadium full of people. If it's Beaver Stadium, Penn State, Ohio State, the entire stadium is packed with 100,000 people, all shoulder to shoulder, tightly packed in there. That means high density. Same thing for molecules. If we got a lot of molecules, they're all tightly packed together, that's high density. Okay? Low density. An example we can all relate to right now when we're on quarantine. We've all heard of social distancing, staying 6 feet apart. If you have a stadium, Penn State's playing, let's say, Clarion University first week of the season, stadium's maybe half full, you got some people over here, some people over there, they're spread out, that's low density. So if you have molecules that are spread out, They're socially distant from apart from one another. They're low density. So water that we're using today has higher density. It's tightly packed together, its molecules, than vegetable oil. Vegetable oil has lower density. It's not as packed together with its molecules. So that's one reason. The other reason why oil and water do not mix is because of something called polarity. So if you've learned about magnets in school, you know that they have polar opposites or attractors. Okay, so if you have a positive magnet, a negative magnet, you put those magnets together, opposites attract one another. Okay, if you have two positive magnets, they repel one another. You have two negative magnets, they repel one another. Oil is very unique in that it's non-polar. It does not repel, it does not attract, it just comes to a screeching halt. So if I took this water and I put it in this bottle and I mixed it with Kool-Aid, the entire thing would turn red because the polarity in the two, it will mix everything together, it will all turn red. If I put water in this bottle, vegetable oil in this bottle, you would expect that the whole thing would turn yellow, the color of the vegetable oil. It will not. The water and oil will stay separate because of density and polarity. So let's try it out. First thing we need to put in our bottle is water. You can fill this about 2/3 full. The easiest way to do this again is in a kitchen sink with a faucet. That looks pretty good. We got about 2/3 full. Set this aside. And then we want to go about 1/3 full of vegetable oil. Again, pouring this in the sink is your best option. Also, for you little ones, if you have a big glass jar or something with a wide opening at the top, it makes it easier to pour. So as you can see, let's get our cap back on the bottle. Oh. As you can see, the water and oil did not mix, thanks to density and polarity. All the water's at the bottom, all the oil's at the top. Now watch what happens if I slowly flip it over. They still don't mix. You still have the water and oil separate from one another. And as many times as you do this, it will always remain separate. Okay? Let's put that back in here for a second. So to make this a little more fun, to make some nice colorful bubbles when we have our reaction, we'll put in some food coloring. So today we're going to use blue. The darker colors tend to turn out better. I usually do about 10 big drops. 10 to 15 big drops. It will take a few seconds for the food coloring to drop, to settle. So we're going to let that sit there for a moment. Let the food coloring drop down. And color our water. Am I doing okay, Jameson? Does it look pretty good to you? That looks pretty good, huh? Again, if we slowly turn it, you'll notice it does not mix. You may need to add a few more drops of food coloring. If the food coloring doesn't drop down right away, you can add a few more drops. Usually 15 at the most is plenty. So while we're waiting on that, just to review, Once again, the requirements for the Cub Scout Nova Science everywhere is what we're working on, and the requirements are 1C, which is an hour of reading and watching anything related to science. This will be part of that time. And also 3A-5, which choose a scientific question you'd like to investigate and explore it, which our question today was, why do oil and water not mix? Okay, so our food coloring has settled to the bottom. So we'll put the cap back on there. Set that aside for a moment. And we'll grab some Alka-Seltzer tablets. So when we drop an Alka-Seltzer tablet in, it will cause a chemical reaction that will cause the colored water at the bottom to bubble up through the top and return to the bottom again. And that reaction will happen as long as the tablet has not dissolved. So what I like to do is break the tablets up into several pieces, break it in half for today. That way you can do this more than once from each tablet. Now, there is something to be said for the more of a tablet you put in, the bigger reaction you get. So bigger bubbles. So if you put a whole tablet in there, you're going to get really big bubbles. If you put a quarter of a tablet in there, it'll still bubble, just not as big and not as long. So depending on how many times you want to do this, if you've got 4 tablets at home and you want to sit all afternoon and do this, break them up into tiny pieces so you can keep doing it. If you want to just do it once, go big and go home, put the whole tablet in. That works too. So we'll put half a tablet in here. And as you can see, the reaction is almost immediate. We have a lava lamp with some nice colorful bubbles. Pretty fun stuff. And like I said, you can do this as many times as you want. Just when the tablet dissolves, put another tablet in. Everything I showed you here today, water is free out of your faucet at home. Vegetable oil, Alka-Seltzer tablets, food coloring, all those items, if you don't already have them at home, you can pick them all up for less than $15, probably less than $10, depending on the size of the vegetable oil that you get. So it's a cheap activity, it's a fun activity, it's something you can work on at home. And if you participate in this, if you make a lava lamp, we would love to see them. So here's what I'd like you guys to do. If you try this at home, if you make a lava lamp, I'd like you to video it, send it to me. You can email it to me at josh.woods@scouting.org and have some fun with it. If you're okay with it, we would love to share your videos with other scouts to inspire them to work on this activity from home as well. So thank you. Thank you for Mr. Jameson over here. He thinks it's pretty cool. And stay safe, everyone.